Hello physicists, we are going to take a look at string and pulley problems here. I'll jump right in. So this is a sort of class of dynamics problems. It's a early look at like a system analysis, and it's a way we can kind of dig into what's going on with tension in moving systems. So there's a couple tricks to it, and I'll talk you through them. So when we have two objects that are attached to each other by a string, as always in physics, we're trying to simplify things down. And so some of the things that we assume is that the pulleys are frictionless, the ropes that are tethering them together are massless and aren't stretching throughout. So just kind of simplifying things, saying, okay, we've got two objects, they're attached to each other, and they're pulling on each other. We're not getting into whatever rotational momentum might be happening in a pulley of a certain mass. You'll have time to do that in the future if that's your passion. So the first thing, is how do we draw these things? And I've got a little sketch of a free body diagram here, and you can see we've got a mass on a surface, a rope going over a pulley, and another mass hanging there. Now, of course, because they're attached together, the two things are going to accelerate at the same time. The surface could be sloped like this, and we have a directionality or a presumed directionality to the movement of the system. Some problems you may not be sure which way is it going to go. Is this mass going to pull that one down the system or not? When you get going, establish a direction that's going to be positive. And this is the weird thing, or the unintuitive thing. We're talking about the direction of the system. So for this object here, moving up the ramp would be its positive direction, which that direction would mean for this hanging object here would be going downwards is going to be the positive direction. So we're calling this movement the positive direction. You could also, if you're pretty sure this thing is light and this heavier one is going to be pulling it down that way, you can say, okay, well, let's call to the left, up and to the left will be positive, which means when we're talking about this object moving down the ramp would be positive, and for the hanging object moving up would be positive. So you assign a direction to the system, and if you're analyzing individual components of the system, you stick with that direction. You can have two masses hanging over a single pulley, and we call that an Atwood machine. Again, we would have a directionality to this. Positive direction would be up for this mass and down for that mass, or vice versa, but it's the direction of the system. Remember that. Okay, so here's an example. We've got a 0.6 kilogram toy car that's on a table attached to a string, and the string rests over the pulley. We've got a 0.9 kilogram ball attached to the end of the string. Find the acceleration of the car. So there are a few ways we can look at this. I've drawn a little sketch here, and I've put some circles around it. So if we were wanting to find the tension in the string, it would be an internal force if we look at the whole system, in which case we might want to look at just the car or just the mass, or we can look at the whole system. And you'll get familiar with these, and you'll see sometimes you want to do one and sometimes you want to do another. In this situation, we're being asked, what's the acceleration of the car? So we've got a mass accelerating the car, and of course the mass also needs to accelerate itself. We're going to look at the system as a whole here, the blue circle, which means the tension that's inside, those are internal forces. They're not going to be acting on the system. There's going to be one tension going up and one going down. They would cancel out in terms of this system. So if we were to draw the free body diagrams here, we'd assign a direction, and we'd see, there's a force of tension going this way and an equal and opposite force of tension going that way. Those are going to be internal forces, but what we do have is a normal force acting on the car and a force of gravity acting on the car, and we've got a force of gravity acting on the hanging mass. those will be the external forces. So we start out, like every dynamics problem, with a statement of net force, the thing that's always true. And here, the net force is going to be all those external forces that are acting on the system, namely the force of gravity in here. Well, and there's no friction. So I guess that's pretty much it. I mean, we can look at the force of gravity. Come back. And the normal force, those are going to be equal and opposite there. But what we have here is in the x direction, the external force is really only the force of gravity. But here's the catch, is when we're talking about the mass times acceleration that's getting accelerated, there's two masses that are getting accelerated by gravity. If this wasn't attached, we'd still have F equals ma acting on this one ball that's got mass. But now that force of gravity that's tugging down on the ball has to accelerate the ball itself and the car. And so in here, when we're saying, okay, what is the mass that's being accelerated? It's going to be the sum of the two masses. Whereas the force that's doing the acceleration, it's just that hanging mass there. So that's why on the left we only have m2, the 0.9 kilograms, whereas in here, the ma, we're going to have 0.9 plus 0.6, we're going to have 1.5 kilograms. And so following through the math here, oh, look at this, how I've rearranged the equation before putting numbers in. Isn't that nice? Oh. Okay, so that's one type of problem. That's one approach. Realistically, that's kind of one part of a bigger problem, because often we'll be asked what the tension is. Oh, here's a fun little simple one. It's actually a song about this. And so we've got a mass on a table, and we want to know there's friction now. And we've got the mu is 0.5. How heavy does the dead fish need to be to drag the can of Spam across the table? Burning questions. Everyone wants to know. So we set up a free body diagram. We say what's going to be our positive x direction here. And we'll make that the direction of movement. So just like last time, we have a force of gravity that's going to have to accelerate two masses. But this time we also have a force of friction. And so if we take a look at the box in the y direction, we're going to need some y direction stuff because we've got friction. We're going to need the normal force. And we can do a quick analysis and say, all right, the net force is going to be 0. It's not, this box is not accelerating down into the table or up off of the table. So in the y direction, this box has no acceleration, and so the normal force will be equal to the force of gravity. Nice to clear that up, because when we take a look in the x direction, in order for this thing to slide, the force of gravity coming off our dead fish here, which I'm calling object 1, is going to have to be, or sorry, I'm calling that object 2, is going to have to be greater than the force of friction on object 1. So if we just follow that through, we see, okay, the force of gravity acting on here is going to be the fish's mass, which will be the unknown we're looking for, times the acceleration due to gravity. And that needs to be bigger than the force of friction on the box, which is calculated by mu Fn. So then we follow through. We're looking for m2, and we rearrange, and we find a value that for a 20 kilogram mass with a force of friction of a coefficient of friction of 0.5, it would have to be at least 10 kilograms to make it slide off. Example 3. So we've got our same situation, the block on the table with the mass hanging off of it, and now we have friction on this one. So similar to the last example, except here we know the masses and we're finding the acceleration. So we start off, as we start off every dynamics problem, the statement of net force, a statement of Newton's second law, F equals ma. So all the forces here are going to contribute to some mass and acceleration. The forces that we have are the force of gravity pulling down and the force of friction resisting. And the masses that are getting accelerated are 0.9 kilograms plus 0.6 kilograms. So then we just fill in for the force of gravity, that's going to be mg on the 0.9, and the force of friction is going to be mu mg on this one, and I showed why it's going to be mu mg because the normal force is equal to the force of gravity. Showed that over here in green. Rearrange the equation and we get a value for acceleration. It's positive because we're calling over and down the positive direction. One more example. Okay, so now we've got our blocks, again, 0.6 and 0.9 kilograms, but now we want to know what is the tension in the string. So tension didn't come up before because it was an internal force. If we want to find the tension, we need to make it an external force, and we do that by how we define our system. If we make our system just this mass, then there's going to be a force, an external force acting on it. That tension is going to be pulling it here. There's not going to be an equal and opposite one on this block. Or we could also take a look at this dangling mass here and say, all right, we're going to have the force of gravity pulling down and a force of tension pulling up on that. So I've got the two free body diagrams for each of those systems here, and I'm going to show that it doesn't matter which one you choose, you'll still get your answer. Now, because we've already done the problem, we've already looked at the system as a whole and determined the acceleration. Now we can use that information because we know the acceleration of our object. So taking a look at the hanging mass here, we've got gravity pulling down, tension pulling up, and we've got an acceleration. So we can start off with our statement of net force. And when I look at this, I'm going to call up the positive direction and down the negative direction. So my acceleration then is going to be negative. And I can write that in right beside the free body diagram. I've got my information here. So next step after saying F equals ma is, well, what forces are there? There's tension going up and there's gravity going down. So it's negative. And that equals ma. And remember, that acceleration is going to have a negative value. So then rearrange the equation to solve for what we're looking for, the force of tension. Do a little algebra to tie it up, pull the mass out of there. And so we're going to have that 0.9 kilograms times the acceleration, -5, and gravity is 9.8. Why is the acceleration negative while the gravity is not? I attributed the negative to my force of gravity up here. I could have also put the negative up here at this level. It's important that you only do it once. If I said gravity is going down and therefore is negative here, and then put another negative in here at the 9.8, I'd get the wrong answer. So doing this, I get a force of tension of 4.3 newtons. Can also take a look at doing it over here where we've got a force of tension and a force of gravity and a force of friction. We have one extra force here, so it's a little bit more work, but it can be done. This case we would say, all right, F equals ma. What forces do we have? We've got tension and friction going against it. So force of tension minus the force of friction, and that's going to equal mass times acceleration. And so rearranging, tension's going to be mass times acceleration plus mu times the normal force is going to be the force mg. And we get the same answer. So either way, and you should get the same answer. The tension should be the same in each rope. I guess I should really put in a directionality to it. It's a force, so in this case the force of tension would be upwards, and in this particular one the force of tension would be to the right. I guess it's not as important to give a direction to the tension in a rope, because obviously it's in the rope and it goes in both directions. So that's a quick run through of approaching the string and pulley diagrams, of which you have a few practice problems in section, on page 120. Give those ones a try.